Hello guys, this is Prime Concept. In this video, we want to consider a very important aspect of physics, which is considered under mechanics in physics, so which is vectors. So we'll be studying vector analysis. Now, if you were privileged to study further mathematics in your secondary school, you would have also learned vectors a little. So, but then if you were not opportune to learn that, this is a nice opportunity for you to learn the concept of vector analysis, which is very important to us. So we're going to expand on the concept of vectors in this video. If you have been watching my videos and you are yet to subscribe, please do well to hit the subscribe button, like the video, comment, and then share with your friends. Now let's move on. Physical quantities in physics, every kind of quantity you talk about in physics is actually referred to as physical quantities. So what are physical quantities? Physical quantities in physics are quantities that can be measured and then assigned a unit of measurement. So all the quantities you can measure in physics, you refer to them as physical quantities, which would include things like distance, acceleration, velocity, force, momentum, and so on. All these parameters we talk about, they are called physical quantities. Now, based on direction, whether these quantities have direction, we can classify physical quantities into two broad categories. So you can classify them based on their direction into two broad categories. So, and those two categories by which you can classify physical quantities, one is what we know as vector, vector quantity, and number two is what we know as scalar quantities. So these are the two, excuse me, these are the two classifications of physical quantities based on direction. Now, quickly, what are vector quantities? Vector quantities, which is the focus of our study, but I'll explain the two and then we'll go back to the focus. Vector quantities are quantities that have magnitude and direction. Vector quantities are quantities that have magnitude. Magnitude means size, and then they have direction. So these are the quantities we call vector quantities. To make it clear to you, now say I have an arrow like this with an arrowhead. Now, if you see something like this, you can quickly tell that this is actually facing forward, is going forward, right? Yeah, so this quickly gives you the direction and then gives you the size. The size means the length, right? So this is actually how we denote vector quantities. Vector quantities tells direction and they also give the size or the magnitude. And if I draw something like this, you can also tell that these two vectors have same direction. Both of them are facing forward. But then the difference is that they have different size or magnitude. This one is longer than this. So you can agree with me now that vectors have length, or you can say size, or you can say magnitude, and they also give what? Direction. So these are vector quantities. Now, what are examples of vectors? We're going to list a few, not limited to this, but one of them is displacement. Displacement is a vector quantity. Another one is velocity. Velocity is a vector quantity. You need to know these things. Exam can just ask you, one of the following is not a vector, so you need to know these things. We also have acceleration, is also a vector quantity. We have force, is a vector. We have momentum, is a vector. We have torque, is a vector, etc. There are so many, but at least these examples are very important for you to know: displacement, velocity, acceleration, force, momentum, torque. These are all vector quantities because they have direction, which is the special ingredient. Now, the second we said is scalar quantities. Scalar quantities. Now, what are scalar quantities on the other hand? Scalar quantities are quantities that have magnitude, but they don't have direction. So they have magnitude, but no direction. That is to say, if I draw a line like this, now you can quickly notice that this particular line has a length. So this is the length of this line. But you can't tell where this line is facing. You can't tell if it is facing forward or facing backward. So you can tell that since this does not indicate direction, this represents only what? Magnitude. So that is what scalars are. Scalars are quantities that would only give you the size, but they can't give you direction. I can still have another one like this. You would also see that there's a difference between both of them. This is longer than this, so meaning that the size or the magnitude of this is greater than that of this. But where are they pointing? We don't know. There's no direction. Or with this, you can tell that they are pointing forward. So scalars have magnitude, but they don't have direction. So examples of scalars you need to know includes distance, would include speed, would include power, would include work done, so and so on, would include, okay, etc. So these are examples of even temperature and so on. Temperature, there are so many we can list, right? So these are examples of scalar quantities. They have magnitude, but they don't have direction. Now let's come back to our topic of interest, which is vector quantities or vectors, vector analysis. So that is what we are considering. So quickly, vectors. Remember, we've already established the fact that vectors have magnitude and direction. So in this video, we'll be learning how to work with the direction signs for vectors. So very fast, we want to learn the representation of vectors. How do we represent them? Now, we have two major ways of representing vectors. There are so many ways for advanced levels, but for 100 level physics, second year physics, we'll be looking at just two major ways of representing vectors. Number one is what we call Cartesian or rectangular or standard representation. So that is number one. Is either you say it is Cartesian representation, or you call it rectangular representation, or you call it the standard representation. Now, what is the Cartesian representation? Cartesian representation considers the coordinates x, y, and z. It considers the coordinates x, y, and z. So whenever you see them in terms of x, y, and z, it means that that representation is in the Cartesian coordinates. Now, let me make it easy for you. Before now, from your O level, for example, say you want to plot graph. They can give you a point, say point A has coordinates, say 2, 3. You can see something like this, right? Which would simply tell you that in the Cartesian plane, and the first number here is on the x-axis. The second number here is on the what? On the y-axis. So, but we have a different way of representing this, still saying the same thing, but we now introduce the vector directions to make it even more easy for us. Now, instead of writing like this, we now have a new way which we call the Cartesian representation. So which is given as this. And whenever you see an alphabet with an arrowhead, it simply tells you that that alphabet is actually a vector. So the standard way to represent is this: AXI plus AYJ plus AZK. So this is how we represent vectors in Cartesian coordinates. And what does AX AY and AZ represent. AX, AY, and AZ are the components. They are the components of the vector. They are the components of the vector in X, Y, and Z axis. They are the components of the vector in X, Y, and Z axis, respectively. So that is it. Then whenever you see I, J, and K, what do they also represent? I, J, and K are called unit vectors. We'll still learn what unit vectors are. They are called unit vector in X, Y, and Z axis or direction axis, respectively. So what it means is that whenever you see I, it tells you that that particular component is in the X direction. Whenever you see J, that component is in the what? Y direction. Whenever you see K, that component is in the what? Z direction. So these are unit vectors. They are actually referred to as unit vectors. We'll still learn what unit vectors are, but they are referred to as unit vectors, and they indicate the direction in which that particular vector is pointing. I'll give you a quick example. So we have vector A, we have something like 2i plus 3j minus 4k. Now, it simply means that since I have I attached here, it means that the number 2 is the component of this vector in what direction? In the X direction. So if they ask you find the component of this vector in X direction, I would simply say it is AX as a component of A in X direction, and AX is equal to what? 2. If they say we should find the component in the Y direction, I would say it is AY, which is equal to what? 3. If they find the component in the Z direction, I would say it is AZ, which is equal to what? -4, not just 4, -4. Now take note, when you're getting components, you don't carry I, you don't carry J, you just pick only the coefficient of I, that is the component. The coefficient of J, that is the component. The coefficient of K, that is the component. So these are the components of vector A in the X, Y, and Z direction, right? Yes. So this same thing you're seeing here, say you don't want to write it this way, you can just quickly see this is what. Remember, this 2 is in which axis? X. So I can write this by saying 2i, then plus this one is in Y, right? I can now say 3j. So this is another way of writing this, what we learned from secondary school. So that is just vector notation. That is how vectors represent these things in Cartesian coordinates. Cartesian coordinates. So let's look at number 2 method of representation. Number 2 is what we know as polar form. Polar representation. What is polar form? Polar representation uses the magnitude and an angle as the direction of the vector to represent that vector. It uses the magnitude and an angle to represent the vector. So it uses magnitude and an angle to represent the vector, and that angle, the angle is the direction. So the angle talks about the direction of the vector. Now, how do we represent vectors in our polar form? And this is how we represent vectors in polar form. Say we are given vector A like this, then in polar form, this would be this at an angle theta. So this is how we represent in polar form, where this represents magnitude, which is the next thing we're going to look at. Whenever you see in physics, especially in vectors, you see an alphabet enclosed by two straight bars. This is called magnitude of the vector. Magnitude of the vector. So we'll soon learn how to find magnitude of a vector, which is very simple. Then theta is the direction, which is actually the angle direction of the vector. Now sometimes they still use, some books decide to use another symbol. Rather than using this, they can just use R. So you should know that R, which stands for resultant or magnitude, is same as this. So instead of writing like this, they can still write like this, R at an angle theta. So what is an example of a vector in this form? You can be given vector A equals 3 at an angle of 30 degrees. So this is an example of representation in polar form, which we would see how to analyze both in Cartesian form and also in what? Polar form. So take note of these notations or symbols. Now let's quickly learn how we can find magnitude of a vector. So since we have already introduced magnitude, how do we find magnitude of a vector? The magnitude of a vector, very simple. Quickly, the magnitude of a vector is a positive quantity. The magnitude of a vector is a positive quantity. That is to say, the magnitude of every vector can never be negative. Magnitude is a positive quantity that is obtained by the relation. So this is how we find it. So, and first you should know that whenever you see bars, this thing means magnitude. And magnitude of a vector is usually gotten from the Cartesian coordinates. So it's going to be ax all squared plus ay all squared plus what now? Az all squared. So this is how we can find magnitude of a vector. Now let's take a quick example. Say vector A is equal to 2i minus 3j plus 4k. So we have this. Find this. This is how exam would ask you. They will just say find this. They won't say find magnitude. They just say find this. So you should know that this thing means magnitude. So quickly, let's see how we can solve this. So the magnitude, which is denoted by this, is going to be the square root. Now remember, it is ax squared. And what is our ax here? Our ax is the one attached to I, which is 2. So I'll say 2 all squared. Notice I'm using brackets so that I don't confuse it. This must always be plus. It can never be negative. So plus, my next is negative 3. I'll put it in a bracket again. Negative 3 all squared. So even when you're punching with your calculator, put them in bracket. Otherwise, it will give you a wrong result. Then plus, this must also be plus 4 all squared. So what do we have in this case? 2 squared is 4 plus 3 minus 3 squared is 9 plus this, which is 16. So I have 9 plus 16 is 25 plus this 29. So I have the square root of 29. So this is my answer. So this is the magnitude of this vector. You can see it's very simple to find. Now let me give you another problem. Now, example, vector A equals I minus 2j, comma, find 2 times magnitude of A. Find this. So it's still very simple. So one of the first things you want to do when you have a problem like this, they say find 2 times magnitude of A. What do you think we should do first? First thing is to find the magnitude of A. then we multiply by 2. Okay, let me make it 2 questions. So find magnitude of A minus 4. So say we have these two things to solve. Now let's start with the first. First thing first is to find magnitude of A. And magnitude of A is square root of, what is the coefficient of I? It is 1. So I would say 1 squared plus, what is the coefficient of J? It is what? Minus 2 all squared. So I have square root of 1 plus 4, which is going to be square root of 5. So this is magnitude of A. And the first question says find 2 times the magnitude. So it's going to be 2 times magnitude is going to be 2 root 5. And this is our answer to the first one. Now for the second one, it's to find magnitude minus 4. So it means that our magnitude we already have as root 5. Magnitude of A minus 4. This is simply going to be, the magnitude of A is root 5, then minus 4. So if you evaluate this root, you can get your answer and subtract depending on how your options are in the exam. So this concept of magnitude, I believe it's simple and very clear. And let's move to the final thing we'll be analyzing in this video. Then we continue in the next video. So we'll quickly conclude this by defining a unit vector. Remember, we've already mentioned the idea of unit vector. So we're going to define that in this video and take an example. So unit vector. Anytime you hear unit means 1. So it should be clear to us. Now, a unit vector is a vector whose magnitude is 1. A unit vector is a vector whose magnitude is what? 1. So this is a vector whose magnitude is 1. Or you can say its magnitude is unity. That is a unit vector. And a unit vector, it gives the direction of a vector. It gives the direction of a vector. Now say you have something like this. This is x and this is y. The unit vector that tells us that something points in the x direction is what? Is I. So it means that I is the unit vector that talks about what? The x-axis. So unit vector gives direction. So I tells us that the direction is along the x. Then the unit vector that gives direction of y is what? J. Now what if we have a vector that lies between this plane and this vector is A? So how do we know this direction? The vector that gives us this direction is a unit vector, which we will now denote with the symbol A cap. So A cap is a vector that tells the direction in which this A is pointing, which is neither this nor this. So this is what we mean by unit vector. So I is a unit vector, J is a unit vector, which we already know their axis. Then this is also a unit vector whose axis is somewhat between this other axis. That is what we mean by a unit vector. Now there is a confusion that usually comes from this definition, which I want to clear. Now we said that a unit vector is a vector whose magnitude is 1. Now a lot of people may think that a unit vector is 1. A unit vector in itself is not 1. It is the magnitude of a unit vector that is what? 1. So a unit vector is not 1. Rather it is its magnitude. It is its magnitude that is 1. So it is not the unit vector that is 1. It is the magnitude of that vector that is 1. So how do we find a unit vector pointing in a direction of a given vector A? So the unit vector in the direction in the direction of A. The unit vector pointing in the direction of A is usually denoted by A with this cap above it, and it is equal to the vector A divided by the magnitude of the vector. So this is the formula you can always use. If you're talking of B, you can just say B, which is vector B over magnitude of B, and so on. So this is how we can find a unit vector. So we'll take a quick example under that. I'll take two examples. Unit vector, one straightforward and one applied question. So quickly, given vector A equals I plus 2j, find the unit vector of A. So we want to find the unit vector of A. Now from our formula, you will quickly see that for you to find unit vector, the only thing you need to find is magnitude. Once you get magnitude, you are done. So let's start by solving for magnitude of A. Now, A is I plus 2j. And what would the magnitude of A be? The magnitude is going to be the square root. The coefficient of I is 1, so I would say 1 squared. Please notice that when we're finding magnitude, we don't use I, we don't use J, we take their coefficient. So then plus the coefficient of J is 2 all squared. So what do I have here? I have square root of 1 plus 4, which is the square root of 5. So it means that the magnitude of that vector is root 5. So if that is the case, then I can find the unit vector using my formula, which is vector A divided by the magnitude of A. So what is our vector A? Our vector A is I plus 2j. What is our magnitude? Our magnitude is root 5. So this is our answer. But for the sake of maybe objective exams, we can split this. We can say the magnitude is going to be 1 over root 5i plus 2 over root 5j. We can still write it this way depending on how they want your option to be. So this is our answer or this. Now we want to verify our claim. We are done with this problem already, but remember our earlier definition, we said a unit vector is a vector whose magnitude is 1. Now, since we've gotten this unit vector, let's see if this is actually true, if the magnitude of this vector would be 1. So let's check. For confirmation, this is how we can find the magnitude of this unit vector, which is going to be square root of the first component of I. Coefficient of I is 1 over root 5 all squared plus coefficient of j is what? 2 over root 5 all squared, right? So this is going to give us the square root of, now watch, this square would affect this square root, so you'll be left with 1 over 5 here. So I have 1 over 5 plus this square would affect 2, it becomes 4. This square would affect this square root, you're left with 5. So that when you add up what you have in that root, you'd have 4 plus 1 by LCM. By LCM, 1 plus 4 is 5. So it means that we'll have the square root of 5 over 5. Now what is 5 divided by 5? It is 1. So I have the square root of 1, and the square root of 1 is what? 1. So you can see that the magnitude of this unit vector A is equal to what? 1. So you take note of that. A unit vector is not 1, rather it is the magnitude of the unit vector that is what? 1, just like we can see. So I want to give a last question, an applied question here, before we now end the video. In my next video, I'll be doing very important things under vectors. We're looking at addition and subtraction of vectors and the law, parallelogram law of vectors. So do well to subscribe to this channel so that you'll be updated when I post new content. Now, given that given that A equals say 0.5i plus lambda j is a unit vector, find the value of lambda. So this is an applied question. Now they are telling us that this vector, which is equal to 0.5i plus lambda j, is a unit vector. Now, if it is a unit vector, find the value of lambda. Now, how do we approach this question? We simply approach it by knowing that for a unit vector, its magnitude is 1. So since this is a unit vector, we want to find the magnitude, then equate it to 1. So let's do it. The magnitude of A is going to be square root of 0.5 squared plus lambda squared. This is the magnitude of A. Since A is a unit vector, it means that this magnitude should be equal to 1. That is the property we know for a unit vector. So I can quickly see that I would have square root of 0.5 should be 0.25. 0.5 square should be 0.25. 0.25 plus lambda squared. This is equal to 1. So quickly, I want to remove, because I'm trying to find lambda, so I need to remove this square root. So I'll square both sides. I'll square both sides so that this square will now cancel this. I'll be left with 0.25 plus lambda square equals, now 1 square is still going to be 1. So I have lambda square equals 1 minus, when this crosses, it becomes minus 0.25. So I have lambda square equals, this is going to be 0.75. So 0.75. Now, so that my lambda becomes the square root of 0.75, of course, plus or minus square root of 0.75. So this is actually the value of lambda when you evaluate that square root. Then you found the value of lambda. So you see how exams can come with applied questions from what you've already learned. So I'm going to come to an end with this point. So in my next video, I'll be analyzing addition, subtraction of vectors, and then parallelogram's law of vector, which is very important for you to know. And then the next video will be looking at resolution of vectors. So we'll have a good number of things to learn on that vectors. So do well to subscribe to this channel so that you'll be notified when I post videos. Like the video, comment, and share with 10 of your friends. Tell them this is Prime Concept. Thanks for watching.